Okay, so why is it called shooting method? Well, first of all, this will become obvious once I show what it really does. So here we treat the dynamics as a black box. Okay, now if you wrote the equations of motion using Python, like we've done, you have access to the equations and you can discretize the equations of motion, right? That's what we did in the collocation method. But what if you use the simulator like Coppelia Sim? You do not have access to the equations of motion. You don't see them. They're inside the simulator. So if the equations of motion are hidden from you, you cannot open them up. You cannot open up the simulator sometimes. In this case, a shooting method is good. So what it does here is it treats the dynamics as a black box. So let's say these are the dynamics. Example would be the simulator which we use. What you can supply to the simulator is the initial state. You can initialize the position. You can initialize the initial velocity. You can also supply it with controls. You can specify alcohol controls U0, U1, so on till UN. So you can supply it n controls. And what comes out of this would be it will give you the position at time t and x2 as time t. So it gives you the position velocity, right? It can give you all that at every instant of time, whichever instant you have. Now this, you don't have equations are just unavailable. So you can only observe the output and you can give in inputs, which tends to be controls, but you do not have access to the equations. Actually, the equations for this are pretty simple, right? X double dot equals u. But just because it's hidden inside the simulator, you don't see them. Okay, so here is what we can do. We can specify x's, we can specify u's, and we go from there. We just use with the limitations posed by the tool we use. So let's do shooting method. So as I said, there are three things we need to specify in any optimization method. Those are, we've done this in the past, the optimization variables, the cost, and the constraints. Once we have these three things, we can put it in SciPy minimize and go from there. So let's see how to frame all those things for the shooting method. So the first thing is the optimization variables. Here, as I said, you cannot control the dynamics in the sense you don't have access to that. So what we do here is we say that we'll choose the time because we can send when to stop the optimization. We can also input the controls. Okay, that's about it. So what we have here is there's 1 for the time. This is going to be 0, 1, 2, so on. So it'll be, if you look at these, you count them, it'll be n plus 1, right? Because the 0 index goes all the way to n. So the total number of variables are n plus 2. Okay, you can contrast this with what we had in the past for collocation. So for collocation, we had t, we had u, but in addition, we also had the position velocity, which is not available now for shooting method. So next is the cost. Okay, the cost is simply the time, which is optimization variable, which is easy. The last one is constraints. Okay, so we know the constraints are the initial position is 0, the initial velocity is 0, position we know that we also need to set the position at time t equals t, and time should be d, and d is usually given to us, and then x2 at time t is 0. Now, here's the thing, which is because we can set the simulator in whatever state we choose to, we can actually pre-specify these things. These are just specified, or you can say initialized in the simulator. For example, in Copilot Sim, we can set the car to be at 0 speed and at 0 position, and you don't have to worry about them. So we end up with just two constraints. So we can do the math here again. Optimization variables, we just said it's n plus 2. It's right here. And then constraints are 2, which means that the free variables are n plus 2 minus 2, which is n. So you still have n numbers you can tune. Okay, so if you compare this against this method, the collocation, we ended up with 3n plus 4 optimization variable, 2n plus 4 constraints, and still had n. A lot more things to deal with compared to shooting method. Okay, so we've set it up. We just need to put it in. Once we have set this up with these two things, we need to go to Python and do the use SciPy optimize. So here is well, this was code for do collocation, and maybe since we already got it to work, let me just run that first. So this is collocation we did last time. I think I set it to run. Here, let's try again. Okay. Then it should show up some plots. Because you said it's like 100 last time. Yeah, I think I made it to 20 back. Yeah, thanks. Yeah, so I didn't make 20. It should be fast. So, okay, so this is basically showing the position, velocity, and the controls, in this case, brake or acceleration. So starts from 0, goes all the way to 5 in this case, d is 5. I did not specify the units, in about 2.23 seconds. So that's the minimum time. Okay, so with acceleration of 5 and deceleration of 5, it looks something like this. You go full throttle. This is actually a discretization problem. It shouldn't be minus. You don't start braking when you're accelerating, so it should be +5, and then I should brake, right? But half the time, it's about a little more than half, maybe. This actually should be shifted a little bit. I mean, there are some issues with discretization. So this is what it looks like, and this relates to our experience. There is, yeah, this should be more or less a ramp, so it should be vertically down. And as you make the grids, I chose 20 grid points, which means that I chose 20 intervals from 0 to 2.23, but you could choose 100 and it'd be much more smoother. Will be much more what we expect in the reality, right? So let's stop this. Let me show the shooting. I use actually, there's two codes. One of them uses a solver called SLSQP. This is called sequential quadratic programming. And the other one uses the trust constraint. They are in the same toolbox, minimize, SciPy optimize, minimize, but they differ in how they want you to specify the constraints, cost, and so on. Okay, so the first thing here is that there should be a simulator which basically thinks of the whole thing as a black box. And I should have like a, a simulator of some sort. So I have something called simulator. What the simulator does is if I send in the initial position and velocity, z0, then it basically, and of course x is the controls, and the grid points, it basically simulates this ahead of time and sends in output, which is basically the entire time history, the entire position velocity history, and the entire control history. So that's like, you could replace that with Copilus and it'll work just as fine. Okay, so that's that. Now we can go and look at uh, the function minimize. Okay, so minimize is what is it doing? It's basically using the cost. There is a initial guess. There's a method, constraints. The optimization constraints are when you want it to terminate the optimization, and then the bounds. Okay, so let's look at each of these. You can start from the top. This car is, I think it just does the animation. If I'm not mistaken. I think it just does the interpolation. And where, see where it is called car. Yeah, I basically, okay, so the car is just a function which this is just the integrator. This basically integrates the equations of motion. I didn't have to have it separately, it just does dz dt. The dynamics of the car, in this case, it's a double integrator. So the cost is the first input. So remember, I need to send the optimization variables into x. So time is one, the first one, and then everything is controls. The first one is time, so x0. The nonlinear function basically gives me, there are just two nonlinear constraints. One is the end position, which is x end, and the end velocity. So the end velocity should be 0, and x position minus d should be 0. So that's all the constraints. The bounds, there's a bound for time, 1 through 5, and then minus 5 to 5. Many times these bounds, if you give the bounds to be minus infinite, well, for this is okay, you have constraints in the car, but if you give 1 to infinity or 1 million, right, what will happen is the optimization might actually get stuck in some of those regions where you shouldn't want it to. So your best bet is to start with a smaller bound and then see how the optimization proceeds. Let's say I chose 1 and 2. And then if you found it's hitting one of the bounds, that means that bound is too close to the optimum and you need to shift it, and you just have to keep doing it. That's why something like this is, again, it's an art. It's not a sort of engineering more than science. You need to keep trying different things for different problems, and that's how they work. Okay, this is the initial start point. U is the initial start. I assume all the controls to be 0. Bounds, and then equality constraint. This is just prepackaging it in the language of SciPy opt minimize, and let's just run it. And then once it runs, I just test it out. Let's see what we get for. Okay, so here it's a little bit better than what we had for collocation. You can see that, so x dot u, x is position. I need not close it. So let's just go here, run it again. Okay, now we can look at x dot position velocity and u. Position starts with 0, ends with time distance equals 5. The time is about, right, 2.23, I think. That's what I got earlier. It should be very close to that. It should actually be something which is, yeah, it says 2.013. That's the time. And then the good thing here is that it actually gives what we wanted. Earlier, it was started at -5. That did not make sense, but it starts with acceleration, goes there, and then deceleration. And then you can see this is a result of that discretization because of the point. So if you want a better solution, all we do is go and change this. So I just put 5. 5 is not enough. Let's do 20. Like the same as we got, I put for collocation. Is it running? No, it's running. Yeah, it's taking some time because it's 20 grid points. Okay, there it is. So here's a solution for 10 grid points. You can see that the x is actually much smoother than previous what we found. Profile looks almost similar. There actually should be a ramp down, should switch, but because of the discretization, it chooses to do that. Okay, so that works. You could also do this with this method, truss constrained. Just the same kind of things are needed, except that they need to be packaged in a different way. Here, you'll see the same things. For example, you'll see car, the ODE, the simulator, uh, the cost, nonlinear functions, which returns the end velocity, position, and so on and so forth. We can run this and see what the results are for the same 5 and 5. Now, this can be made faster if you can specify some of uh, the derivatives, the gradients, the Jacobian in this case. I've not specified any Jacobian, so it's a bit much slower. So something like this, which is slow, you can't really implement in real time. So you need to do these calculations offline and then try to implement them online. The other way is if it's faster, then you can actually do these computations on the fly as the robot is working. And that's become increasingly possible with faster computers and better methods to do this optimization. I have no idea why it's taking so much time though. Should have done the same plots. Yeah, there. Okay, so it's going to quit, but here it goes +5, -5, and similar to the previous one.